In this lecture, we get to start looking at nonlinear problems, which is where things get pretty interesting. And we'll start with the scalar case, nonlinear scalar hyperbolic problems, conservation laws. And so Berger's equation is one that we've talked about a little bit in the past, but I'm going to start talking about a different model that arises from traffic flow, which is very similar to Berger's equation in that it has a quadratic nonlinearity, but it has a little more physical intuition about what's going on that might help us understand what's going on a bit better. So we'll look at some of the key concepts about how shocks form and something called the Rankine-Hugoniot jump conditions that have to hold across a shock wave, and look at some examples for the case of traffic flow in particular. So the idea of shock formation, if we were just solving linear acoustics equation, then we started with, say, a pressure perturbation that looks like this. And zero velocity, we would expect it to move out to both the left and the right as acoustic waves with sort of equal amplitude and simply translating without any change in shape. Or similarly, if we think of this as the shallow water equations and the depth of the water, then in the linear case, if the perturbation were a small perturbation of the background depth, that's what we'd expect. But in the picture I've drawn here, the perturbation is actually quite large compared to the background depth. And so as this starts to propagate out, at first it looks fairly smooth, but then as time evolves, it sharpens up into a shock wave. Each of these two waves that are moving out sharpens into a shock wave on the leading edge, with a smoother rarefaction wave following behind. So in the case of a system of two equations, like the shallow water equations, you typically have two waves, and each one of them can give rise to shock waves or rarefaction waves. And eventually we'll look at systems of nonlinear equations. But to start with, we'll look at just the simpler case of a scalar equation that would model one or the other of these sorts of waves. So each of the solutions in a more general system would kind of behave like what we're going to see for the scalar equation, although not quite, because you don't have linear superposition of waves the same way you do for linear equations. So it all gets much more complicated when we get to nonlinear systems. But to start talking about scalar equations, we're going to look at a simple model for traffic flow. This is a much more complicated sort of traffic flow pattern where we have some traffic jams and entrances and exits and multi-lanes, and people can change lanes, and people do actually try to model this kind of situation with systems of conservation laws where you typically have maybe an equation for each lane of traffic plus some junction conditions where different roads come together. There's actually a pretty large literature on using conservation laws for solving complex traffic flow patterns. But to start with, we're going to look at a very simple case where we just have a single lane of traffic and cars that are just following each other and not allowed to pass each other. So we have the simplest kind of model. Before we even go to the hyperbolic PDE, we can derive an ordinary differential equation model where we just look at capital X sub j as being the location of the jth car at time t on a one-lane road. And we simply have a differential equation that says the time derivative of the position is equal to the velocity, and then we would have some rule for what the velocity of the jth car is at time t. And so to get a simple model, you can assume that the driver adjusts their speed instantaneously depending on the distance to the car ahead. So if they were all moving simply at the same constant speed regardless of traffic, then we could kind of model this with a constant coefficient advection equation for the density of cars. But to make it more interesting and nonlinear, we'll assume that the velocity actually depends on the density, or in this case of this ODE model, it depends on how far the car ahead is. And so as you approach a car ahead, if you get too close, you slow down. Or if space opens up, you speed up. And so that suggests that the velocity can be modeled by something like this. The distance from car j plus 1 to car j times some scalar v. Or sorry, this is some v is a function of this distance between car j and car j plus 1. So v of s is given as some function of s that defines the speed as a function of the separation s between cars. To get a feel for how interesting you can see traffic flow and see in particular things like shocks forming, there's a really nice simulation that you can find on this web page. Let's see if we can go to that here. So if you click on this link, it should take you to a page that looks like this. This has actually been running for a little while, so you can see a shock wave is actually starting to form here. But to kind of keep things simple, let's go to this ring road, this circular road here. And this is still more complicated than what I'm going to talk about because it has 3 lanes of traffic and it has some trucks that are moving at slower speed than the cars, and cars are allowed to change lanes, and so to really model this would require a more complicated system. But you can still see as this starts to evolve that things, even though they started out fairly uniform, you can get shock waves, traffic jams that sort of spontaneously form. So if we wait here another minute or so, we should start to see, here you start to see some congestion. Even though cars are allowed to change lanes, you still get this sort of congestion building up here. And then if you watch it for a while, what you see is that this sort of discontinuity between fairly spread out cars that are moving quickly and much denser cars that are hardly moving at all, there's almost a discontinuity in the density here, which is a shock wave that's propagating backwards through the traffic as more cars join the end of the traffic jam. And then at the front of the traffic jam, cars start to accelerate because the road clears out ahead of them. It's kind of fascinating to watch these, but you can see very clearly that you get a shock wave that's propagating backwards through the traffic in this case. And in the front, as the cars start to speed up, you don't get a discontinuity, but you get sort of a smooth spreading out of the cars, and that's what's called a rarefaction wave that we'll see many examples of as we go on, which corresponds to the fact that the flow is getting rarefied or becoming less dense as you pass through the rarefaction wave. Yeah, so here in this car following model, we're assuming that the velocity of each car is some function v of the separation between cars. And so what sort of function might we look at? Well, here's a typical example. This v of s depends on, here L is the length of a car, and so L over s is sort of a measure of the density. And depending on the density and some maximum velocity, this says that if the cars are sort of bumper to bumper and the separation distance is only L, then the velocity is 0. You stop if you're bumper to bumper. But as the distance between cars increases, going out this way, the velocity increases, but then it asymptotes to some value v0. Oh, sorry, that's the same as u max, which is a maximum velocity that you would like to go at if there's no cars in front of you, which might be the speed limit or whatever your desired maximum velocity is. So we can define a local density based on the separation between cars relative to the car length. And so the way it's defined here, that would be between 0 and 1, with 1 corresponding to bumper traffic and 0 corresponding to an empty road. So if we want to go to a conservation law now in a PDE, we want to switch to a density function. So here I'm going to let Q represent the density of cars. That'll be the variable in our scalar conservation laws. And we'll normalize it now so that the units that we use for x along the road is in units of car length. So for example, x equals 10, a distance 10 corresponds to 10 car lengths away from the origin. And the units we'll use to measure Q will be in cars per car length, so that we'll again have Q between 0 and 1, this density, 0 corresponding to empty road, 1 corresponding to bumper cars. And so with this density, then the total number of cars in an interval can be modeled as the integral from x1 to x2 of this density function with respect to x. Of course, the actual number of cars should be some integer, but when we look at sort of the big picture and zoom out of it, this is a representation of the density. And so in the usual way that we've derived in the past, we end up with a conservation law where the flux is simply the velocity multiplied by the density. That's the rate at which cars are going past a point with the units that we've chosen, and the conservation law is dq dt plus f of q dx equals 0 in this PDE form. But now, rather than u being a constant velocity, as we had in the advection equation, instead the velocity is some function of the density. So some function capital U of the density q. So in particular, to sort of match the car following model that we were just looking at, we might choose u of q to be some maximum velocity, the speed limit, say, times 1 minus q, where q again is the density. And so that would give us a flux function, f of q then, that's this velocity, capital U, multiplied by q, and that gives us u max times q times 1 minus q. So it's quadratic in q, similar to Berger's equation, where the flux is just 1/2 u squared for ut plus f of ux equals 0. It's quadratic. It's got a different sign on the quadratic term, and that leads to a slightly different character of the shock waves. But it's basically the same sort of equation as Berger's equation. But it has a little more physical meaning, perhaps. So if solutions are smooth, we can use characteristics to solve the problem. So if we start with the PDE form of the conservation law, if we assume things are smooth, we can further write that as in this quasi-linear form, qt plus f prime of q x equals 0. And then we can define these characteristic curves that are curves capital X of t, whose derivative, x prime of t, is equal to f prime evaluated at whatever density q occurs at this particular point, x of t at time t. Okay, so if we start with x at time 0 being some little x0, and then we solve this ODE forward in time, and each time we, assuming we know the solution q at xt, we can evaluate q at wherever x of t is, comma t, evaluate f prime at that point, then that traces out some curve in xt space. And the reason for defining it that way is that if we now look at how q varies along this curve, if we take the time derivative of q at x of t at time t, well, t appears in both of these variables, so we have to take the x derivative times x prime of t plus the time derivative to get the full derivative with respect to time. But now using this assumption for the characteristic curves, this x prime of t is just f at q of x of t. It should be f prime of q of x of t. There's a prime missing there. But that then gives us qt plus f prime of q times qx, and that's exactly what the PDE form up here says should be equal to 0. Okay, so what we end up with is that along these characteristic curves, there's no change in the solution. The solution is constant on characteristic curves. Just like in the advection equation, in that case, the characteristic curves were all parallel, moving at speed x prime of t equals u, some constant value, and whatever initial data you have simply translates along those parallel curves, straight lines. But even in the nonlinear case, we still have this property that as long as the characteristics don't intersect each other or cross, which we'll talk about in a moment, as long as things stay smooth, the solution is constant on these characteristics. And moreover, since the solution is constant on the characteristics, and since we're evaluating f prime, should be f prime at q on the characteristic in solving this ODE up here, if q is constant on the characteristic, then so is f prime, and so is x prime, and so the characteristics are still straight lines in the xt plane. So if we draw the xt plane, start at some point x0, and solve this differential equation, assuming the solution stays smooth enough, what we'll find is that the characteristic curve is a straight line, and the solution is constant on that straight line. In the constant coefficient advection case, if we started at a different point, we'd get a characteristic that's parallel to that, and everything simply shifts at the same speed. What's different now in the nonlinear case is that if you start at a different point, the characteristic curve, it will still be a straight line, but it will have potentially a different value because f prime of q might be different for the q that's constant along that line. So they might be spreading out as we vary the initial position, or they might be coming together. And in that latter case is when we run into problems and have to start talking about shock waves. Okay, so if we go back to Berger's equation, which we'll talk about for a moment just because it's a little simpler to work with the flux function. So the flux is again a quadratic flux, but just 1/2 u squared. In quasi-linear form, it looks like an advection equation, but with the solution advecting with speed u. So the characteristics are constant, have constant slope equal to u, and the value of u is constant along each of those characteristics until you potentially have a shock forming. So if we look at it in this form, and suppose this is our initial data, then each value of u that we have here, u starts at 1 and goes up to a value 2 and back down again. So if we start at some particular point here, if we started at this point, for example, then the slope would be 1 of this characteristic curve, whereas if we start here, the slope would be 2, and the value would be constant equal to 2 along that characteristic curve. Or another way to look at it in this sort of frame in which we're looking at the solution as a function of x, as it starts to propagate, the peak is traveling at velocity 2, whereas this point down here that's only halfway up the peak, where the value of u is 1.5, it's moving only at speed 1.5, and so it's moving more slowly. And so as time evolves, the peak is moving faster than the rest of the wave, and we get this steepening of the wave on one side and spreading out on the other side. And if we just keep following this picture, then eventually we get sort of an overturning of this wave and a triple valued solution. And if we're thinking of this as representing the density of cars or the density of gas or depth in the shallow water equations, then it may not make sense to have a triple valued solution, at which point we really have to replace this with a shock wave. And then to replace it with a shock wave, it turns out that the right criterion to use, if you take this triple valued solution and cut it off with the shock wave here at some point, is that the area that we cut off here and the area that we cut off here should be equal. And the reason is that the area under this curve, at least as long as it stays single valued, the area under the curve is always constant because it's a conservation law that we're solving, and the area under that curve is the total integral. And you can show that even after it starts overturning, the area that's sort of underneath this deformed curve has to be equal to the original area. So if you're going to take the triple valued thing and replace it with a single valued function that has a discontinuity, then the area under that new wave with the discontinuity in it also has to be equal. So we have to cut off equal amounts on either side in order to conserve mass, basically. Another way to look at it a little more mathematically maybe is that we can think of taking the Berger's equation and adding some viscosity to it, as I've talked about before, turn it into a viscous equation, which is a parabolic equation, and you can show that this equation has smooth solutions for all time from any initial data. So with the initial data we were looking at a moment ago, it wouldn't overturn. Instead, it would just steepen up, but the amount of steepening would be limited by the viscosity, and then you can look at the limit as epsilon goes to 0, and it becomes steeper and steeper. So why would we try to solve the hyperbolic equation if this parabolic equation has fewer difficulties with triple valued solutions and whatnot? Well, again, solving the parabolic equation directly typically requires an implicit method, and there's often some physical velocity, which is why this makes sense, but the physical velocity is often so small that we can't possibly resolve the details in the sort of the viscous shock profile properly. And so trying to solve the parabolic equation doesn't necessarily give you a better physical solution, but it gives us a way mathematically to think about what is the approximation that has a discontinuity in it, what's the right place to put that discontinuity, and what's the right sort of limiting solution of this viscous equation as the viscosity vanishes. So again, we've seen this picture before, but this is just a viscous advection equation with a small parameter epsilon, and as epsilon goes to 0, the solution to that converges to a discontinuity, and similarly for Berger's equation, and you can use that also to figure out what's the right location for a discontinuity. We can also define what's called a weak solution of the differential equation. Remember, when we first looked at deriving these equations, we really started by deriving this integral form of the conservation law, that the rate of change of the total mass between 2 points was related to the flux at the left minus the flux at the right. And then, assuming things were smooth, we could manipulate this into the differential equation form. But if we don't assume things are smooth, then this integral equation form makes sense in situations where the differential equation doesn't. The integral equation form doesn't require differentiating q directly with respect to either x or t, and so we don't have to worry about the fact that there might be discontinuities in the solution where those derivatives don't make sense. So if you take this integral form of the conservation law and now integrate it in time from time tn to tn plus 1, then integrating this time derivative just gives us the difference between that integral at time t2 minus that integral at time t1. And then if we integrate the fluxes on the right-hand side here in time, we get an integral in time of the flux at the left edge minus the integral at the right edge. And we've also seen this form before. This is exactly how we defined a finite volume method, except that we now divided by delta x here, so that this 1 over delta x times the integral was the cell average at the advanced time, and we could write that in terms of the cell average at the original time and integrals of the flux at the two edges over the time period that we're looking at. But again, this form at the top here can also be used in cases where you can't use the differential equation directly. Or there's another way to look at it that's actually easier to work with mathematically sometimes, and that is to define what's called a test function, phi of x, y, that's smooth and can be differentiated, and that has compact support, meaning that it's identically 0 outside of some finite interval. And then take your original, or not really the original equation, but the differential form of the equation, qt plus fx equals 0, and multiply it by this smooth function, and then integrate in space and integrate in time over all space if we're doing the Cauchy problem, and over time 0 to infinity if we're doing an initial value problem starting at time 0. And again, this test function phi is chosen so that it vanishes when t is sufficiently large. So these integrals here, even though they're over infinite domain, they really reduce to integrals over a finite region. And the function phi is smooth. So what's the advantage of doing that? We still have the derivatives on q and f of q here, which aren't smooth. But now we can integrate by parts, and we can move those derivatives from q and f of q onto phi. And by assuming that phi vanishes far enough out in both x and t, when you integrate by parts, all of the boundary terms vanish out where absolute x is large and where t is large. And the only place that you get a boundary term in the integration by parts that doesn't vanish is at t equals 0. And that's the term that shows up here on the right-hand side. So this is at t equals 0, you have a boundary term which involves the initial conditions q of x at time 0 and whatever this function, your test function, was phi at time 0. But now this form of the conservation law says that no matter what test function we take, if we take any test function phi that satisfies these conditions, we can test whether q times phi t plus f of q times phi x integrated over this domain is equal to this integral based on the initial data. And if that's true for all test functions that have compact support and that are smooth enough that we can differentiate phi with respect to x and t, then we say that q of xt is a weak solution of the differential equation. And certain proofs of properties of differential equations or numerical methods sometimes rely on this definition of what it means to be a weak solution of the conservation law, because it doesn't require Q to be smooth. We've put the smoothness restriction on this test function instead. So it turns out that if you look at a solution of a conservation law that's piecewise smooth and that has jump discontinuities, so as a function of x, it might be something like what we were looking at before. It has maybe a nice smooth part of the solution and a discontinuity. It could have, much more complicated structure, maybe several discontinuities, but it's smooth in between the discontinuities. It turns out that if you sort of analyze when can a solution like that be a weak solution in the sense of the definitions we just looked at, either in terms of a test function or in terms of the integrated form of the conservation law, in order to be a weak solution, in the regions where the solution is smooth, where you can differentiate, it turns out the PDE has to be satisfied in the ordinary sense. So the idea of a weak solution is really an extension of the ordinary strong solution idea that it actually satisfies this conservation law in terms of differentiating Q. But if they're jump discontinuities, then there's some additional conditions. There you can't differentiate Q. So there's another set of conditions that have to be satisfied across any jump discontinuity. And it turns out there's a very nice sort of formulation of what the jump conditions have to satisfy in order for a piecewise smooth solution to actually be a weak solution of the conservation law. Oh, let me also note, though, that the way we've defined weak solutions, it's not always true that there's a unique weak solution, as we'll see, especially in the case of rarefaction waves that can form from a discontinuous initial data. There may be more than one or even infinitely many functions that are weak solutions in the sense we just discussed. And then we have to impose some other conditions to figure out which is the one that's really sort of the physically correct one, by which we often mean the one that you would get if you took the viscous equation and let the viscosity vanish. So there's kind of often a unique physical solution based on that vanishing viscosity idea, but the weak solution definition doesn't necessarily pick out that solution. It may allow other solutions, and so we need some other methodology to deal with that, which we'll look at later. But for now, we're going to take a look at this Rankine-Hugoniot condition, which is the condition that has to be satisfied across a jump discontinuity in order to be a weak solution. And the idea here is that we're going to look at the xt plane, and we're going to zoom in on a shock wave that's propagating along with some speed s in the xt plane. So again, this is t going upwards, x going this way, and we've zoomed in on a bit of the shock where it's essentially moving at constant speed. It could be varying speed with time, but if we zoom in on a very small region from x1 to x1 plus delta x and from t1 to t1 plus delta t, then we can assume, to order delta x and delta t anyway, that to the left of this shock wave, q is essentially constant at some state ql, and to the right of the shock wave, q is constant at state qr. And then we can look at what conditions have to be satisfied in order for this shock wave or a discontinuity moving at this speed to be a weak solution of the conservation law. And we can do that by looking at this sort of integrated form of the conservation law, which we've seen before. So if we look at integrating the conservation law over this rectangle, then what we have here is the integral of q at the advanced time minus the integral at the original time is the difference in the fluxes. And so if we assume that our box is small enough that q is essentially ql and qr on the two sides, then at the advanced time, this integral, the state is essentially equal to qr. So we should get delta x times qr. So actually there's a minus sign wrong in this equation, because we should have delta x qr at the top, whereas the integral at the original time was delta x times ql. And then when we integrate at the left side, we'll get delta t times f of ql, and we'll be subtracting off the integral on the right side, which is delta t times f of qr, plus higher order terms that are order delta t squared if we zoom in enough and things are smooth. Now, if we divide by delta x, or by delta t, I guess, and take the limit as delta t goes to 0, then delta x in this particular figure is really minus s times delta t. All right. Delta x is minus s times delta t, the way I've drawn this figure. So when we divide by delta t and let delta t go to 0, then this term actually becomes plus s. So the sign is correct on this last equation. So it's s times qr minus ql is equal to f of qr minus f of ql. So the upshot here is that if we have a shock that's propagating and we zoom in on what speed is it propagating at around a location where things are smooth away from this discontinuity, what we find is that the shock speed has to be related to the states QL and QR just to the left and the right of the shock by this relation at the bottom here, which is what's called the Rankine-Hugoniot relation. So it says that the speed times the jump in Q has to equal the jump in flux, and that's required for any discontinuity that's propagating in a weak solution of the conservation law, because it's required simply by the conservation condition. So in the case of a scalar equation, you can just solve for s. So you could take any two states, QL and QR, evaluate what f of QL and f of QR are, and you could have a solution that has a discontinuity with that jump propagating at the speed s given by the Rankine-Hugoniot condition, which for a scalar equation you can compute like this for any q left and q right. However, when we look at systems of equations, it gets a little more complicated, because in the system case, QR minus QL and also f of QR minus f of QL are both vectors. So whereas s, the shock speed, is a scalar. So this equation at the top here says that some scalar multiple of this vector with m components has to equal this other vector with m components. So that gets more complicated. We've already seen a particular case of that for a linear system of equations. For a linear system of equations, we have f of q is just a times q. And so f of qr minus f of ql is just a times qr minus ql. And so that says that a times qr minus ql has to equal a scalar multiple of qr minus ql. Well, that's exactly the condition that says that the jump qr minus ql has to be an eigenvector of the matrix A, and S, the scalar, has to be the corresponding eigenvalue of the matrix. So this condition that we've seen for linear systems, that every jump discontinuity has to propagate with a speed that's some eigenvalue of the coefficient matrix, and the jumping Q across the wave has to be a corresponding eigenvector, is just a special case of this Rankine-Hugoniot condition for systems. For nonlinear systems, though, it gets more complicated. So here's a picture of shock formation with going back to the traffic equations in the case where we have some cars that are forming a traffic jam. And so we've started at the bottom here with some discrete set of cars, and the figures on the left sort of show discrete cars and how they might propagate. So this figure here shows actual particle paths, or the paths that these cars might take as they accelerate or decelerate. And at some later time, we get this sort of pattern of cars where we have nearly a jump discontinuity in the density. And then on the right, we have the corresponding continuum model where we have a density function that's smooth to begin with that represents this distribution of cars. And here, what I'm showing is the characteristic curves, these curves that satisfy f prime, x prime of t is the flux function prime evaluated at q of x of t. So those are the characteristic curves. And on the next couple of slides, I kind of zoom in a bit more on each of these figures. So in the case of the actual car trajectories, what you're seeing is that a given driver out here where traffic is light is moving along at some speed, but eventually they sort of catch up with the traffic jam and then they slow down. And so these are the trajectories of individual cars. And a car that starts out over here has clearer road ahead and would be speeding up as time goes on and spreading out. And so we get this sort of bunching up and shock formation around here where the discontinuity appears and this sort of spreading out on the other side. In terms of the characteristics, we end up with this picture then where we have actually a shock wave forming at this location and the smooth rarefaction wave following behind here. If we plot the characteristics, again, these are the characteristics now in the xt plane, remember that away from the discontinuity, the solution is constant on characteristics and the characteristics are straight lines. So each one of these lines here is a straight line, and if you start with at any particular point, look at what the density is there, the density stays constant on that line, and so the slope of that line stays constant as well. But if you start over here, then that characteristic curve eventually may collide with a characteristic curve that's coming from the other side. And so if you looked at a location here, you could trace back along the characteristic and see what the solution is. If you start any place over here where things are smooth, you can also trace back along some characteristic. Wherever you start, you can trace back along a characteristic, and since the solution is constant, if you're in these smooth regions, you can actually reconstruct exactly what the solution looks like by tracing back along characteristics. But there's this singularity here where the characteristics come together, and that's where this shock wave is forming, and it's moving at some speed, which, as we see in this figure, isn't necessarily constant. It starts to curve because as this shock wave propagates, well, the way I've taken the data here, the value on one side is always constant, but the value on the other side is actually decreasing with time, because if you look at what's happening on the right here, when you follow back these characteristics, you're getting different values as you trace them back. And so the value just to the right of the shock wave is actually decreasing as time goes by, and therefore the strength of the shock is decreasing, and the speed at which it's traveling also decreases, and so the path that the shock follows is not a straight line. It's curved because at each instant in time, its speed has to satisfy the Rankine-Hugoniot condition based on the values just to the left and just to the right of the curve at that particular time. So let's finally just finish this lecture with the simplest possible case, which is the Riemann problem, which is our sort of building block for doing more complicated things. So as usual, if we start with initial data that's simply a single jump discontinuity from some density q left to q right, and again for the traffic flow equations, we're assuming that there's some desired velocity u of q that each driver drives at that depends on the density, some u max times 1 minus q, and the corresponding flux is simply q times u of q, which is this quadratic function in q. And for a scalar conservation law, there's typically, for the Riemann problem, really only two cases to consider. One is if QL is less than QR, and for this traffic flow problem, if it's less dense to the left than the right, then the speed at which people want to drive on the left is greater than the speed on the right, and that's when you have sort of a traffic jam, that cars are approaching this traffic jam and suddenly have to slow down. And so we expect a shock wave in that case. The other case is if Q left is greater than Q right, so it's denser on the left than on the right, and so the speed people want to go is smaller on the left state, than it is in the right state. And in that case, the cars that are sort of close to this interface can accelerate and start to move faster, and so in this case we expect a rarefaction wave to come out of this Riemann problem solution instead of a shock wave. So here's just a couple of particular cases. If we look at a case where Q left is less than 1, but QR is equal to 1, which again means bumper-to-bumper traffic. So to the right, cars are not moving. Here's the picture down below at the initial time You've got a bunch of cars sitting at a red light, say, but you have other cars that are approaching them in this left state where the density is less than 1, and so those cars are moving at some speed. But as they approach the end of this line of cars or the traffic jam, they have to slow down, and so you get a shock wave that sort of naturally forms. In terms of the characteristics, again, the characteristics, since we have just two constant states, QL over here and QR over here, the characteristics are not only straight lines, they're all parallel, with the speed u of QL on the left, or not u of QL, but rather f prime of QL on the left, and they're all constant with speed f prime of QR on the right, but then in this case they're impinging, and we have to insert a shock wave. And at the shock wave, the Rankine-Hugoniot condition has to be satisfied. So since the states to the left and the right of the shock wave are always QL and QR, the speed at which the shock wave in this case is going is also constant. That's a straight line, and it has this constant speed. And for this particular data here, that speed is negative. But if I'd taken different data, if QR weren't 1 but were a smaller value but still greater than QL, then you can potentially have a shock wave that moves to the right if all of the traffic is moving, but it's moving faster in the left state than in the right state. You can still have this sort of shock wave forming, but the shock wave could be moving with the flow, and it could be moving either slower than or with a negative speed like we see here, or it could be moving with a positive speed. And the other case that we'll talk about more in the next lecture is sort of complementary case if we start with initial data where it's bumper to bumper to the left, but there's no traffic at all to the right. So that would be like a line of cars that are sitting at a stoplight that turns green, and now when it turns green, the first driver can immediately drive off at the speed limit, Umax, because there's nobody in front of them. But the second driver doesn't immediately drive at that speed because the density or the separation between that car and the leading car is initially bumper to bumper, and only slowly does it grow. So the velocity of the second car actually starts out at 0 and then speeds up more slowly. And so each subsequent car gets started a little later, as we're familiar with from sitting at red lights. And so you get a rarefaction, but it's a smooth rarefaction. You don't have a jump discontinuity in the density. Well, I guess you go from density 0 to a very low density here, but when we look at it in terms of the conservation law, it's a smooth function. And again, in terms of the characteristics, if we look at the characteristics in the xt plane, we've got all the characteristics to the left in the left state have slope f prime of QL. All the characteristics over here have slope f prime of QR, and f prime of QR is larger than f prime of QL for this problem. And so you get this sort of spreading out. And the correct solution, the one that sort of matches our intuition here and the picture that's on the left, is in between these sort of limiting characteristics that are determined by the initial states. In between, there's a smooth fan of characteristics, an expansion fan or a rarefaction fan. But as we'll see next time, you could also put a discontinuity in here that satisfies the Rankine-Hugoniot jump conditions, and it would still be a weak solution of the conservation law. It just wouldn't be sort of the physically relevant one that we want to find. So we'll talk more about this next time.